Hello and welcome to the lecture of linear algebra. And before we start the new topic in this lecture, I just want to briefly revise the topics that we studied in the last lecture because they are very important and they need to be thoroughly understood before we start discussions over new topics which are coordinate systems or dimension of vector space. Um, as we already defined the linear independence, that from the perspective of the vector space, that if there are p vectors in vector space and they are said to be linearly independent if and only if the linear combination of those vectors when put equal to 0 only present us with the trivial solution, which is c1 equals to 0, c2 equals to 0 and cp equals to 0. Now if any one of them is non-zero, the resultant is actually a linear dependent set, and so uh, any of the variables c1 0, c1 c2 cp, any variable which has a non-zero value when solving this above equation will lead to a linearly dependent set from v1 to vp. Now to give you an example on that, just say that a single vector in is linearly dependent. You can say that single vector is linearly dependent if and only if it is not equal to 0. But if there are two vectors, uh, they said to be linearly dependent if one vector can be written in the form of other. Similarly, we can continue this process, and we can say that if v1 to vp are the index sets of vectors in v vector space, then vj and vj is some vector which is the linear combination of the other vectors, then this is a linear independent set. Okay. Now similarly, the one of the example of a linear dependent set is the polynomial vector space of nth order. So for example, if p1t is equals to 1, p2t is equals to t, and p3 of t is equals to p2 of t is equal to 4 minus t, so you can see that I can write this p3 of t as nothing but a linear combination of p1 of t and p2 of t. It means here c1 and c2 are presenting, so if I say this is c1, this is c2, so it means c1 is equals to 4 and c2 is equals to 1, indicating that they are non-zero values and thus presenting us with a non-trivial solution. Okay. So one of the very important example is sine of t and cos of t. So they are a linearly independent set because sine cannot be written in terms of cos and cos cannot be written in terms of sine. Now at least from the perspective that you cannot have this sine of t plus c1 times sine of t and c2 cos of t equal to 0. Okay. So you'll find that c1 equal to 0 and c2 equal to 0. Okay. Similarly, but if you say sine 2 of t is equal to cosine of t into cos of t into sine 2 of t, but we already know that sine 2 of t is equal to 2 times cos of t into sine of t. So we know that v2 is equal to 2 times v1. So we can actually say that here that c1 is equals to minus 2 and c2 is equals to 1. Okay. Now from the perspective of a subspace, right? So if I say HB is a subspace of in some vector space V, and B is some index set of vectors B1 to BP in V, then this set of vectors form the basis of the vector space that they are a linearly independent set. Okay, so it means B is a linear independent set, and the span of B1 to BP actually is the vector space H, right? Now the question arises that one of the vectors might not be linearly independent. So in that case we have to use the set spanning theorem, but that discussion will just follow in the next slide. So generally a basis of V is linearly independent set that spans V, okay, because we know that V is a subspace itself. So V is a vector space, so it is also a subspace itself. So if A is an invertible matrix, so for example here, if A is an invertible matrix, column of A forms the basis of R of n. So in this case, if A is invertible matrix, it means the column space, the space formed by CL of A, actually these columns will form, the columns of A will form the basis of the vector space formed by CL of A, right? And they actually span R of n. So because they exist in n dimension, so if there's m cross n cross n matrix, so they span R of n. Okay. Now one of the examples of again the linearly independent vectors in Rn is this is the columns of the identity matrix, so which is E1, E2 and En, as you already discussed earlier. Now once we know that, right, we can actually find the vectors in a vector space, or the basis space, or the basis vectors that may be independent, but there may be cases in which some of the vectors may not be independent. It means these vectors can be written in the form of the already existing vectors in the vector space. So for example, if I say so for example, an example like this, if say v1, v2 and v3, but we can see here that v3 can be written in the forms of v1 and v2. So in generally, if these three vectors span a subspace H, right, so because v3 is nothing but a linear combination of v1 and v2, we can actually, this span of v1, v2 and v3 is nothing but span of v1 and v2. And since we know that the basis is an efficient spanning set that contains no unnecessary vectors, so it has to be a minimum set of vectors that can span the vector space. Okay. So if one of the vectors in S, say vk, is a linear combination of the remaining vectors in S, then the set formed from S by removing vk still spans H. So that's one of the examples that we just did, that since there were three vectors and one of the vectors were linearly independent, we removed that v3, and this v1, v2 vector still spans this vector space H, subspace H, right? So if and the second part is, if H is not equal to 0, some set of S is a basis of for H. So it means if H is not purely a null space, there might be some set of at least one vector that forms the basis of for H, right? Now we did some examples on this very concept, and that is given the slide as well. So today we'll talk about the coordinate systems, and it is quite important in a sense that when you're studying the vector space and the basis for the vector space, you have to really understand it basically generates a different kind of coordinate system from the one in which we already used to treating the vectors. Okay, now so let's start with coordinate systems. And so what generally it does is basically is if we superimpose let's say a basis B for a vector space V, what it does is impose a coordinate system. Impose a coordinate system which is very similar to, I should say, which is similar to Rn, but might have different orientation. It acts like an Rn. Your book says it acts like an Rn, and Rn, it looks like an Rn, but might have different orientations and projections. We'll see that in just a few moment time what that really means. So so exactly the set of bases B actually provides a new view of V. Okay, so new view of the vector space. So we define first the uniqueness theorem, which says that if B is a set containing P vectors, be a basis, and these are the bases of some vector space V, then for each x in V, a vector x in the vector space V, there exists only unique set of scalar values in which we can say x is equals to c1 b1 plus c2 b2 and cn bn. Yes, sorry, it should be n. Now, so it means the value of c1 is unique, c2 is unique, and cn is unique. Okay. Now, as we have defined, if you remember in our last lectures as well, that if again B is B1 to BP is a basis of V, and say x is in V, the coordinate system relative to the basis V, or the B coordinate of x, are the weights C1, Cn, such that you have x is equals to C1 B1 plus Cn Bn. So what does it really says? It says that if these are the set of basis vectors Pp of the vector space, and of course they are linearly independent, so if there is a vector x in that vector space, we can define a new coordinate system in which the weights or that we have defined earlier actually are nothing but the scaling factors on that new coordinates. Okay, so in general we can say that we can represent x in that beta vector space as nothing but equals to c1 up to cn, and it is we can say it's the coordinate vector of x, and of course because it is for specific set of vectors, so it is relative to B. Okay, so for different set of basis vectors, these might have different values. Okay, so or you can say the beta coordinate vector of x, or beta coordinate vector of x. Okay, and we say anything that transform this x in Rn or whatever the subspace they are n to xp is the coordinate mapping. Of course determined by this value, this set of vectors b. Okay, now to illustrate this by an example, let's say there are two vectors let's say b1 and b2, the basis vectors for for r square. Okay, and we know b1 is actually 1 0 and b2 is equals to 1 2, right? Now suppose an x is in r square, okay, because these are basis vector for r square, and in which has the coordinate vector. So we know that this is the coordinate vector, right? This is the coordinate vector, which is x of b is equals to -2 3. What you have to do is find x. Okay. So what we have been told here is that these are two vectors b1 and b2, which are the basis of r square. Now suppose there's an x vector which is in r square, this is vector space, and whose intercepts on these or intercepts actually, or the scaling factors on b1 and b2 are given by -2 and 3. So if you look at here, this is the value, c1 is -2 and c2 is equals to 3. Okay, so what you have to do is to find x. Remember that from that equation, that x is nothing but equal to c1 times b1 plus c2 times b2, right? So it means here x is equals to -2 times b1, so c2 is 3 times b2, so -2 times b1 is 1 0 plus 3 times b2 is equals to 1 2, and your answer should come out as 1 and 6. Okay, so x is equal to 1 and 6. Okay, now similarly, so this 1 and 6 entries, this x is equals to 1 and 6 are relative to the standard basis, and the standard basis we know that is what is, this is 1 0 and this is 0 1. So this is the other standard basis for r square. So normally what we do is we use this standard basis in our everyday mathematical analysis, that this is the basis vector in x direction, this is the basis vector in y direction, right? So we call this as x 1 0 and 0 1. So x is actually in the standard basis, right? So these are different bases. This is called the standard basis, right? And we can see it quite quickly here, that 1 equals to 1 0 plus 6 times 0 and 1. So these are actually what we call the standard bases, right? So this is the standard base over here, and this is the standard base over here. Okay, now so similarly, now we can actually have a graphical view of the example we just covered, right? So it means if I am looking for this standard basis, this is standard basis, right? Standard basis. We know that from our theory earlier, this standard basis is actually E1 1 0 and E2 is equal to 0 1, or we call this as epsilon E1 E2, right? So this is our standard basis, and standard basis, the value, the x will be 1 and 6. So this, let's say this is 1 unit, 2 3 4, and similarly you have 1 2 3 4 5 6. So 1 6 will be a point somewhere here. So this will be a point x in the standard basis, which is E1 here, and this is E2 E2, right? So this is nothing but, you can say B2 is equals to sorry, not B2, this is 6 times E2, and this is 1 times E1. Okay, so this will be the point in the standard basis. Now look at the scenario in which we have the basis defined by the values as back page 1 0 and 1 2. 1 0 and 1 2. So this is B1 is 1 0 and B2 is equals to 1 2. Okay, So now 1 2. So if I want to draw that basis, that would be, this will remain the same, which is b1 1 0 will remain the same, but b2 is 1 2, right? So I mean, if you look from the conventional point of view, 1 and 2 points on that side, so 1 2, right? So there will be a vector 1 and 2 somewhere here, right? So it means the standard basis for this one is more like this, right? This is b1, this is b2, okay? And now I can actually extend this as a parallelogram, right? Remember this vector theory. So previously this was an orientation which was more like this, right? And now it is more like shifted. So this is b1, this is b2, okay? Now if you see that equation in which you have defined x of b as -2 and if I remember exactly, is -2 and 3, right? So in this one, this is b1, this is b2. So -2 and 3 means here that I have to go to -2 times b1 plus 3 times b2. So -2 times b1 is somewhere here, so -2 times b1, and you have 3 times b2. So this is, let's say this is 1 b2, this is 2 b2, let's say this is 3 b2, right? So this is 3 b2, okay? And now that point would be somewhere here. See, this is x. So previously on the standard axis, the point x is here, and on this axis the point is different, right? So I can draw this to flex it out. Okay, so the point is as reached over here. So standard basis is more straightish and this is like more tiltish, okay? So this is how you can represent x in different bases. This is the x represented in the standard basis, and this is the x represented by the basis for the following vector, following basis vectors, okay? Similarly, now it means so we can talk about the coordinates in Rn and relate to the coordinates in x of in beta coordinate system. So you can say coordinates in Rn, and other one you can say the beta coordinate system. Yeah, right. So it means what we can do is, now if you know the point x over here in standard coordinate, we can actually move it to beta coordinates, and if you have the point in beta coordinates, I actually should be able to find x in the standard coordinate system, right? Now from that, let's say if I have b1 is equals to 2 1 and b2 is equals to -1 and 1 and x is equals to 4 and 5, okay? Now and the vector space beta is equals to b1 and b2, okay? Now what you have to do is to find the coordinate vector. Find the coordinate vector which is x of b of x relative to b, right? So now the question is slightly different, in which we've been given the basis vectors, and we've been given the x in a normal coordinate system, in a standard coordinate system, and we have to find the value of x and b. So we know that it should be c times b1 plus c times b2 is equals to we know that should be equals to x or equals to x from the uniqueness theorem or the vector space theory, because it has to be written in the unique way. So in that point of view, we got here c1 as 2 1 plus c2 as -1 and 1, and we know that x of b is nothing but equals to c1 and c2, right? So this is x. Now once we do that, it means I can write this vector as 2 -1 1 1, and you got here c1 and c2 is equals to x in this case, which is 4 and 5, okay? Now when we solve that, you'll find that x of b will come out straight away as has 3 and 2. Okay, now we can also graphically look at this this problem here, and we can see here in normal coordinate system, which is standard basis, we have 4 and 5. So this was, let's say, 1 2 3 4 and 1 2 3 4 5. So the point was somewhere here, so the point X is somewhere here, okay, in a standard basis. Now this is vector b1 and b2, and you know b1 is 1 and 2. So 1 and talk about, sorry, 2 1, so this is 2 and 1, so this vector is b1 is in this side, and other vector is -1 and 1. So if I extend it here, so this will be, you know, -1 here, somewhere here, right, and 1 here on this side. So it means this point here, so this vector will be somewhere on that side. Now, so this is b1, this is b2. So now what you have done is we have actually shifted x1 standard axis, x1 and x2. Now so it means and when you followed it, and when you solved it, the coordinate relative to b for x we found out to be 3 and 2, right? So this is actually, you can say here 1, you can go here 2 and somewhere 3, right? And for that the second one is 2, right? So 1 2 and 3, let's say, so b1 2 b1 2b1 3b1, and then you have to have 2 b2 on that side, right? So 2b2 will be somewhere, this is 2b2, so b2 and 2b2. So if I had it here, 2b2, it will be here 2b2, right? So in this case this is the standard basis x will remain at the same point, right? But now we are representing x in a different basis, determined by b1 and b2. Okay, so from here we can see that I can transform vector change. Actually, we can change the beta coordinates of vector x into standard coordinates for x, and also we can actually do the opposite way around, right? So we can have the standard coordinate for x, and you can change it into beta coordinates of x. Okay? So from the equation we have just written that if b is equals to b1 to bp, right? So pb is the set of vectors, which is sorry, bn, not bp, bn. Okay, then we can say that x is nothing but c1 times b1 plus c2 b2 times cn bn is nothing but equals to pb, and you got here as x of b. So if you want to get x in a normal coordinate system, what you have to do is to apply this this actually kind of transformation determined by the basis vector bp to the coordinate system determined a coordinate vector of x relative to b. When you multiply them both, you will get the values of x. It is quite evident, this equation is quite evident from over here, what we have just did here, that this is p of b, which is b1 and b2. This was the coordinate values of x of beta, and this was x, right? So just the change orientation of equality, and we had the very similar equation. And so bb actually we can say that is nothing but change of coordinate matrix. Okay, and what it does is basically transforms xb to into x, right? So x of b into x, right? So So PB is the matrix that actually transforms the coordinate system, the vector x relative to b to x in a standard coordinate system, right? Similarly, if you want to go opposite way, right, it means if you want to find out x of b, so that means what you have to do is to do PB inverse of x. So here this PB inverse matrix actually will give you the coordinates relative to b when you are given the coordinates relative to the standard coordinate system. Now this leads to another very important property, because we've been dealing with this kind of transformation in our earlier topics as well. So if I say let b is equals to the set of vectors b1 to bn be a basis of vector space v, right, then the coordinate mapping x to xb is a one-to-one linear transformation from v to Rn. Okay, so that generalizes what we have just discussed in our discussed earlier. But similarly, we can extend this concept in the sense that if I say there is two vectors u and v in vector space v, right, so u is equals to c1 times v1 plus cn times bn, and w is equals to d1 b1 up to plus dn times bn, then you can say that u plus w is nothing but c1 plus d1 times b1 plus cn plus dn times bn. Okay, right, so from that concept here, you can say that uw defined in the space with respect to b is nothing but equal to c1 plus d1 cn plus dn. That will be the coordinates relative to b, right, which can be written as c1 up to cn and plus d1 up to dn. Now c1 to cn are the relative to u, and beta coordinates of u relative to b, and d1 to dn is the coordinate relative to w. Similarly, we can say that r times u, where u is r into c1 b1 plus up to cn bn, can be written as r times u to b. So if you multiply any vector u with r in standard vector space, they get just simply multiplied in the vector space relative to b. Okay, now this transformation we have just discussed, or the coordinate mapping that we have just discussed, it's a very unique example, is a very important example of isomorphism from v to Rn. Okay, and it is a one-to-one linear transformation from a vector space v to the vector space Rn. Similarly, if any transformation from vector space p to another vector space w is called isomorphism from v onto w. Okay, now the thing here is that every vector space calculation in v is accurately can be accurately found in W, and other way around, given by the matrix P of PB. Okay. Now say for example, one example is the polynomial space, standard basis for, let's say, let B be the standard basis of space P3 of polynomials. So let's say B is equals to 1 t squared t cube, and we say P of t is equals to any polynomial of t can be written as a0 plus a1t plus a2t plus a2t squared a3 t cube. So it means this P of t in relative to B can be written as nothing but a0, a1, a2 and a3. Now you can see here the coordinate mapping is from P of t, I can say, to P of t in B with respect to beta, right? And it's an isomorphism from the vector space P3, which exists in space P3, to your onto R4. So this is a vector. These were the vectors in P3. Okay, so these were the standard bases in P3, 1, 2, 3 and 4 and plus 1. And but now these a0, a1, a2 and a3, because they are real values, they are in R4. So it means P3 has actually is an isomorphism from P3 to R4. So this thing here is an isomorphism from P3 to R4. Okay, so what we can do here, that give an example to illustrate what we have just explained. So let's say use coordinate vectors to verify that the polynomials 1 plus 2t square, 4 plus t plus 5t square and 3 plus 2t are linearly dependent in P2. Okay, now thing here is we can now make a very simple scenario. P2 means here is we are just going to have a standard basis as 1 t and t squared. Okay, now with that in mind, we can write this one as nothing but equals to 1 0 2, this one as 4 1 5, and the second is one as 3 2 and 0. Okay, right. So we know that this is a0, a1, a2, a3, but now this was for P3, this is for P2, so the standard bases are 1 t and t squared. Okay, now so we have to find are these linearly dependent or independent, right? So to check they are linearly independent or dependent, what you have to do is just to find out if they have a trivial solution or not. So 1 0 2 4 1 5 3 2 0, and what you have to augment with is 0 0 0. Now we can do here is multiply this one as the 2 and subtracted from here, which leads to 1 4 3 0, and this is 0 here, 0 here, and when you do that, right, so 2 8 minus 3 comes out here, 1 here, 2 here, so 6 minus 6 comes out here. This is 0 and 0. And again we can do the process over here. So if we do the process over here, you get here is 1 4 3 0. Multiply this row with 3 and add it here, so you get here 0 1 2 0 0 0 0 0. So we can see here that the columns of A are actually linearly dependent, and so the corresponding polynomials are actually linearly dependent. So they are linearly dependent, because we can see here that this is 0 over here, so there is at least one free variable, right? So when you know that then there is a free variable, it means it has a non-trivial solution, and when it's a non-trivial solution, the set of vectors are linearly dependent. Okay, and we can see from here as well that your this vector, which is 3 plus 2t, can be written as nothing but 2 times 4 plus t plus 5t square. Okay, so it's a combination of two vectors. Similarly, we can do another example to illustrate this, that let v1 is equals to 3 6 and 2, and v2 is equals to minus 1 0 and 1, x is equals to 3 12 and 7. Okay, so v is equals to v1 and v2. Okay, then we so know that b is a basis of h, which is span of v1 and v2. Okay, now what we have to do is to determine if x is in h. Okay, and if it is, we have to find the coordinate vector of x relative to b. Okay, so in order to do that, right, so first of all you have to determine x is in h. So it means what we are saying that c1 times v1 plus c2 times v2 should be equals to x. Okay, now when we do that, that becomes again as 3 solving an equation which is c1 times 3 6 2 plus c2 times minus 1 0 and 1 and 3 12 and 7. Okay, now when you do that, that leads to the form like that, which is can be written in a matrix form, which is 3 6 2 minus 1 0 1 3 12 and 7. And what you have to do is to reduce into a form which is trying to find if the solution is consistent or not. If the solution is consistent, it means x will be in h, right? So when we do that, right, by a simple manipulation where we convert it to the row operations, the answer we get is 1 0 0 0 1 0 2 3 0, right here. Now what we obtain here is that because this is consistent, we get here c1 is equals to 2 and c2 is equals to 3, and for that the coordinate vector becomes x of b is equals to 2 and 3. Okay, now this is again we can show that in graphically as well. So it means if I say this is x1, this is x2, and this is x3, so the vector v1 is 3 6 and 2, right? So some value 3 here, some value 6 here, and some value 2 here, so the point will be somewhere standard somewhere at this point. Okay, now this will be your v1 this point. Okay. v1, and now this one is the second one is your v2 is actually minus 1 0 1, so So what we're looking at, x1 is the negative side, so -1, x2 is 0, and x3 is 1, so that vector would be somewhere on that side. So this is your v2. Okay, now again, so x is actually 3, 12, and 7. So in standard basis, so which is somewhere 3 somewhere 12, sorry, 3 here, 12 here, and 7, so somewhere on that top here. Okay. Now in the case of the coordinate system relative to beta, we got 2 and 3, so this is we extended here, and this we extended over here, and when we do that we will have find out that this is the point over here, this is the point over here. So this is somewhere, I don't know, this is somewhere v1, this is 2 times v2, this will be 3 times v2, or let's say 3 times v2. Okay. Now similarly we can look at some more examples. Let's say that b1 is equals to 1, 0, 0, b2 is equals to -3, 4, and 0, b3 is equals to 3, -6, and 3, and x is equals to -8, 2, and 3. Okay. So first of all we have to show that b is equals to b1, b2, and b3 is a basis of R cube. Okay. So for these vectors to the basis, they have to be linearly independent, right? So what we have to show here is that they are linearly independent. Show linear independence, which you can do that by putting that in form which is b1, b2, b3, and 0, and start looking for some non-trivial solutions or a free variables. If there are free variables, it means they are not linearly independent. If there is no free variables, it means they are or they end up having a trivial solution, it means they are linearly independent. And the second part is find the change of coordinate matrix from find the change of coordinate matrix from B to the standard basis. So this we can solve it straight away. That it means we know that C1 times B1 plus C2 times B2 plus C3 times B3 should be equals to X. So it means here which leads to equations as 1, 0, 0, -3, 4, 0, and 3, -6, 3. So into C1, C2, and C3 equals to X. So remember that this is PB, right? So this is P beta. So this is PB here is the change of coordinate matrix. Change of coordinate matrix. And the C part is find, write the equation that relates, find or write the equation, that relates x in R cube to x of b, right? That we have already discussed earlier, and that is we can say that x is nothing but equals to p b into x of b. Okay. Now the fourth part, you can find that d is you have to find x of b, right? So what we have to do is to simply solve this equation to find your x of b. Okay. Now similarly we can have last example as the set say the set B is equals to 1 plus t square and t plus t square, and this is a basis for P2, right? So we have to find the coordinate vector for P of t for a polynomial which is 6 plus 3t minus t square. Okay, so this one is quite simple, right? Because what we need to do is simply say c1 times 1 plus t plus c2 times 1 plus t square plus c3 times t plus t square is equals to your 6 plus 3t minus t square. Okay, which if equated straight away by opening the equations up and equating the coefficients of t, constant coefficients of t and t square, leads up to the following equation, which is c1 plus c2 is equal to 6, c1 plus c3 is equals to 3, and c2 plus c3 equals to minus 1. And if you look at these equations here, so you can easily find out that c1 is equals to 5, c2 is equals to 1, and c3 is equals to minus 2. So coordinate system of B is nothing but 5, 1 and minus 2. Okay, now that's the end of this lecture. In the next lecture we'll talk about the dimensions of the vector space and the rank of the matrix. Thank you. Allah Hafiz.